And thank you to the organizers for all just helping me try to get this thing working and for putting this wonderful conference together. And to all the other speakers, it's been a really wonderful event so far. I've enjoyed all the talks. My name is Mc Iver. I hold the dual appointment between the Max Planck Institute for the Structure and Dynamics of Matter in Hamburg, where I'm currently phasing out as an independent research group leader. And I'm now phasing into an assistant professorship at Columbia University. And my group is part of the Max Planck New York Center on Non-Equilibrium Quantum Phenomena, which is a collaborative research initiative between Columbia, Cornell, Flatiron, and Max Planck, where the focus of this center is to study things like non-equilibrium and cavity physics, so very much the focus of this conference. So first, I want to acknowledge my group. So at this point, my group is mostly based in New York, although there still are 6 people in Hamburg, and all the work I'm going to tell you about today was results taken out of the Hamburg lab at MPSD. I especially want to acknowledge my postdoc, Hope Retcher, and PhD student, Gunda Kipp, who are the ones who led the experimental effort. And we also got an enormous amount of theoretical guidance and support from Mario Smykel, who's a postdoc in Angel Rubio's group. And then, Angel was involved, and Guido Meyer and Toru Matsuyama at MPSD helped us with some custom electronics. Michel Sentef, Dante Kennison, and Manuel Baudin also provided various kinds of theory support, and then our HBN comes from the Japanese group at NIMS. So generally speaking, I'm interested in the ultra-fast dynamics of quantum materials. So this doesn't really need much of an introduction for this crowd, but so this is, roughly speaking, say 100 picoseconds to 100 femtoseconds, which corresponds to about 0.01 to 10 terahertz. And the reason that these time scales and frequency scales are interesting is because when you convert this into energies, this is the MeV energy scale where solids tend to show a lot of really interesting physics. And so if you were to do spectroscopy on these time or frequency scales, you can learn a lot about collective modes, energy gaps, superfluid density, and many other things. But on the flip side, because we have so much control with the kinds of laser light we can create now, we can create very strong fields, and we can drive systems out of equilibrium to realize new physics that's interesting to study. And so we've also heard a lot about some of these things today. So photo-induced phase transitions has a long history. There's been a lot of great work done on light-induced superconductivity. Topological flow K-states is an area that I'm also working on, but not what I'll talk about today. And then various examples of ultra-fast control of magnetism, ferroelectricity, charge density waves, and the list goes on. And I think it's fair to say that over the past, say, 15 years or so, there's been a lot of advances in this field experimentally, and this is largely due to technical advances in our ability to do these kinds of measurements. And so we can now create laser pulses going from attoseconds to nanoseconds with central frequencies going from microwaves to X-rays. And this has been complemented by a whole suite of different kinds of ultra-fast probes. And so gone are the days of just simple reflectivity measurements. There's all kinds of linear and nonlinear optical probes, scattering probes, scanning probes, time-resolved ARPEs. But one category that's been missing largely are electrical probes and devices and transport measurements. And this is the sole focus of my research group, is to sort of take these ultra-fast and dynamics of control quantum materials experiments and move them on chip into optoelectronic kinds of ultra-fast measurements. And there's 3 broad reasons why I think it's important to do this. And so the first, for me, this is personally the biggest one, is when you build devices, you have a lot more control. You can build transistors, so you can gate the chemical potential or apply displacement fields or run source drain currents. And now in this new era of van der Waals heterostructuring, we have more control than ever before in the kinds of experiments that we can do. A second big motivating factor is that this can give us access to new kinds of observables, namely transport, which is electrical transport, which is something that's been lacking in the ultra-fast community. And finally, we can always, dream about, ultra-fast functionalities in solids. But what, regardless of whether you think that's, a realistic possibility, one thing that definitely needs to happen, if it is going to be possible, is we need to move these kinds of experiments on chip into the context of devices, and currents and voltages have to be the things that you're working with. So generally speaking, my group is operating at the intersection of quantum materials, device engineering, ultra-fast optoelectronics, and coherent light-matter interaction, because I think at this intersection there's really a lot of room for scientific discovery. Now, the reason this has been challenging to do up until this point is just because the timescales involved far exceed the bandwidth of conventional fast electronics. And so the way that my group gets around this is we are using a special ultra-fast optoelectronic device architecture where the high speeds come from ultra-fast laser pulses, so we can generate, propagate, and detect ultra-fast electrical pulses in these chip scale circuits. For the next few minutes, I'm going to talk just about the circuitry that we're using, because it is kind of a little bit of a unique thing, and this is also sort of the foundation of all the experiments that my group is doing. So at the core of the circuitry is something called the photoconductive switch. This was invented by Dave Austin back in the 1970s. And so what this consists of is an insulating semiconductor patch. And if you were to slap some electrodes on this and apply a DC voltage bias, nothing happens. But if you now shine laser light on this patch that's resonant to the band gap of the semiconductor, you create electron hole pairs, and then in the presence of this DC bias, a photocurrent will flow across the switch. And it turns out that you can operate these switches at very high speeds when using ultra-fast laser pulses, where the time scale is basically set by the carrier relaxation time in your semiconductor. So if you use a dirty semiconductor like amorphous silicon, which is what we use, we can routinely get sub-picosecond current pulses across these junctions. So here's the simplest possible ultra-fast circuit that we could make. So what we have here is one of these photoconductive switches that's biased against the signal line of a microstrip transmission line. So there is a ground line hidden from view, but it's there in the background. And so what happens is if we now photoexcite this switch, it injects a sub-picosecond current pulse into this microstrip transmission line where it begins to propagate. And when this current pulse arrives at this second photoconductive switch here, the voltage profile of this pulse, that is the electric field part of the pulse, transiently voltage biases this switch. And if you photoexcite this switch at just the right moment in time, you can sample the current flowing in your signal line. And then by adjusting the time delay between the generation and the detection laser pulses triggering these switches, you can map out both the amplitude and the temporal dynamics of these ultra-fast current pulses on your chip. So this is not new technology. In fact, we all know Dave Austin and Austin switches from the context of terahertz antennas. But actually, the context in which these switches were invented was in this exact on-chip transport device geometry. It was only later that this was turned into antennas. So it's kind of fun going back to the very original version of this kind of device. So where it gets interesting, though, is not in the circuitry by itself, but when we start interfacing these circuits to quantum materials. And so there are two different ways that we are interfacing these circuits. So the first we like to call ultra-fast transport measurements. So it's basically a time-resolved photocurrent measurement where we take a microstructured quantum material, we ohmically contact it to these microstrip transmission line signal lines. And then we can run source-drain biases. If it's a 2D material, we can we can gate the Fermi level. And then we photoexcite the material, and you can change the wavelength, polarization, and whatnot. And then we look at the photocurrent signals that leave out the different ports of the device, which we then detect downstream using a different photoconductive switch. So we're essentially replacing the generation switch with the quantum material. And so one thing we've done recently in this kind of geometry is we've looked at transport from what's called a flow-K vial semimetal. And so if you take a vial semimetal or a direct semimetal, you shine circularly polarized light, you create these flow-K states. And in the photon dress flow-K band structure that forms, the vial nodes move. And so you can push these vial nodes around the Brillouin zone by controlling these flow-K states with your light. So this is not what I'm going to be talking about today. But what I am going to be talking about today is the other way that we are using these circuits, which is to do on-chip time-domain terahertz spectroscopy on tiny gate-tunable van der Waals heterostructures, and where we're going to be interested in looking at cavity electrodynamics of these kinds of systems. Okay, so taking a step back to the ultra-fast control of quantum materials. So in these kinds of experiments, what we always use are these laser pulses that have an enormous number of photons in them. And the reason that we need so many photons in these laser pulses is because in the far field, the light-matter coupling is inherently very weak. It's set by the fine structure constant, which just happens to be small. So the way we get interesting effects is we just have to use lots and lots of photons. So that's one approach. The other approach, though, is to put a material in a cavity. And so the idea is that with the cavity, you can dramatically enhance the light-matter coupling strength so that you can use much fewer or potentially even zero photons to manipulate the properties of the material. And so, generally speaking, the cavity does at least two things. So one is it increases the probability of interaction because a photon can bounce back and forth many times in the cavity. But the second thing it does is it modifies the photonic density of states, meaning that only certain wavelengths are going to fit inside of the cavity. So at this conference, we've heard about many different exciting possible directions for this new field, and it was mentioned that this is a theory-driven field, and I would agree with that assessment. And there's been many imaginative and exciting theoretical proposals put forth about how you could manipulate all kinds of macroscopic quantum effects using cavities. And there's also been some experiments, especially in bright cavities, and I won't go through the list here because we've actually already heard about most, if not all, of these topics already at this conference. But arguably the most exciting direction for this field is to look at what happens in a dark cavity, where quantum optical effects could be manipulating the ground state physics. And so we heard a great talk from Jerome about manipulating fractional quantum Hall states, where you can now strengthen correlations, which is just really exciting and great because it's a very positive direction of cavity engineering. We also heard a great talk from Daniela about altering the metal insulator transition temperature in tantalum disulfide. The Evison group also has this work on increasing or enhancing ferromagnetism in YBCO nanoparticles, among some other works that were already discussed. But I think it's fair to say that despite these preliminary experimental results, and you'll notice that these are all very recent dates, so it is a new field. What's clear is that more experimental input is needed, just so that the community can gain more traction in knowing what is the right direction that we should be going in, and especially to sort of constrain the bounds for our theoretical colleagues, so that they can give us better guidance. So we could ask ourselves, or I could ask myself as an experimentalist, if I want to do a good cavity experiment, what are the design principles? What should I be trying to do? So if the goal is you want to engineer some kind of macroscopic quantum, response in a material, one thing, while all the details of how all this cavity physics, should work is debated. One thing that everyone can seemingly agree on is that you want to be in what's called the ultra-strong light matter coupling regime. Or at least ultra-strong, or as June said, it could be the ultra, super, mega, ridiculously strong. But the point is you just want to be very, very strong. And so the common benchmark for this ultra-strong light matter coupling regime is if you have a cavity mode that I've shown in blue here, and you bring a matter mode into resonance with it, you want that anti-crossing that forms to be as large as possible, and the threshold to be, in this ultra-strong coupling regime is you want the size of this anti-crossing to be at least 10% of the raw cavity mode frequency. And this is not like a fixed goal, but roughly speaking, if you can get into this regime, this is where non-perturbative, non-linear light matter interaction could start taking place. Rotating wave will break down, things like this. And so this is sort of the parameter space that we want to be in. So this gives us something concrete to work with. So how do we maximize this ultra-strong coupling? So this eta term is proportional to a number of things, depending on details, but two terms that are always there is underneath this square root in the denominator, you have the mode volume and the cavity frequency. So we can already see that if we want to make eta as big as possible, we want to make these small. So two design principles is we want to be working with low energy cavities and low energy physics. And also, if we want the mode volume to be small, we want to be working in sub-wavelength cavities. Because a Fabry-Perot cavity would be the largest possible mode volume where you're in the far field. But if you work with a plasmonic or polaritonic cavity, you can really get this low mode volume and really get these large field enhancements. So that's on the cavity side. What about on the material side? So I think 2D materials are great because they are inherently very exposed and susceptible to their external environment. You can also imagine easily interfacing them with some kind of plasmonic or polaritonic cavity because of their 2D nature. In situ tunability would be great. 2D materials definitely have that. Large lattice constants could be important because generically speaking, light matter interaction goes up when you have large lattice constants. Another way of thinking about it is that large lattice constant means small Brillouin zone. So in like a Pyral's case, your K minus EA, you're going to move a larger percentage of your Brillouin zone for a given vector potential size. And finally, strongly correlated phases are definitely worth targeting because it's been known for a long time that these kinds of phases are always very susceptible to external stimuli. So the punchline here is that I think all of these quantum phases that have been observed in systems like twisted bilayer graphene are really ideal candidates for cavity control experiments. Their energy scale of this physics is 0.1 to 10 MeV. This is this gigahertz to terahertz energy scale, so we're working at low energy. They're 2D, in situ, large lattice constants. It checks all of these boxes. So I'm not saying this is a comprehensive list of design principles, but these are definitely things worth considering, and I do really believe that these kinds of systems are going to be great for these experiments. So this does raise a few challenges and questions. So the first question is, well, what is the cavity? So how are we going to put these heterostructures in a terahertz cavity? So I'm not going to answer that right now, but I'll answer that in about 3 minutes. I am going to answer the second question, though, which is how do we capture these terahertz electrodynamics? Because the problem is, these things are really small. These typical van der Waals heterostructures are on the order of 5 or 10 microns, which is orders of magnitude smaller than these gigahertz or terahertz wavelengths that we're interested in interrogating them at. So that means that we can't use conventional far-field terahertz spectroscopy if you want to study these electrodynamics. We're going to need some kind of near-field technique to do this. And so there's many great near-field techniques to choose from. But the technique that my group's been working hard to develop over the last few years is something called on-chip terahertz spectroscopy. And so with this kind of technique, using these ultra-fast circuits, we can probe the optical conductivity of microscopic samples from 20 gigahertz to a little over a terahertz. We can operate on gate-tunable van der Waals heterostructures in a tunable magnetic field. We can do simultaneous transport measurements, and we can also go down to millikelvin temperatures with this technique. So I'll run you through how this works. So this is a schematic of what our terahertz on-chip terahertz spectroscopy circuits look like. So these are built on a sapphire substrate. Do you have a question? Yeah.
Yeah, sorry. Yeah, sorry. Just can you comment on the temperature, because you have to pump. So how can you get millikelvin temperature and pump with milliwatts at the same time?
Well, very carefully, okay. and we've checked this. And the way we do this is we have my last slide talks about this, okay. But we have okay. But extremely carefully, a lot of engineering has got into this to manage heat loads, and we can maintain, or at least our thermometers say that we're maintaining these base temperatures. Anyway, so okay, so here's how this kind of circuit works. So the basic ingredients are the same as I introduced before. We got photoconductive switches and these waveguides, but this geometry, it's a sapphire substrate, and we are printing both the signal and ground lines in parallel to each other on top of the substrate. In the middle, we have a terahertz antenna, and this terahertz antenna is going to emit a terahertz voltage pulse into these two symmetric waveguide arms. One is left empty as a reference arm, and one will interact with our sample of interest. So let's talk about the sample. And so generally speaking, we are interested in gate-tunable van der Waals heterostructures, as I motivated before. Here's the anatomy of a typical van der Waals heterostructure. You'll have some 2D material encapsulated in hexagonal boron nitride, which is a dielectric, sitting on top of a graphite backgate. Okay, so first, let's just consider what happens if you just take a piece of graphite and we integrate it into this circuit.
So maybe some technical details. So you first deposit the waveguides, then transfer the other way around. But in either case, so are you worried about the strain that is induced by?
No more than any other device physicist would be building these things,
okay.
Let's say. So yes, I'm worried about strain. And so the reason we don't print the waveguides first is because if you have these waveguides that are 300 nanometers thick, and then you put a 2D material on top, it's going to be like the Grand Canyon. This is going to fall in. Also, the top of these waveguides, 300 nanometers of metal is very rough. So it's not ideal. So it's definitely more labor intensive. It's intensive to do it the way we do it, but I'm convinced it's the best way. You build the heterostructure first, then you build the circuitry on top every single time, made to order.
Yeah, and why HBN? Is there any specific reason for choosing HBN?
Oh, just because this is what's by far the best for 2D materials. When you encapsulate 2D materials in HBN, it dramatically improves the mobility. It's a van der Waals material.
So in a sense, but when you measure, you will have your HBN in parallel to your sample, essentially. You will measure the response
right, but the
of the two
terahertz
objects
response of
in parallel.
HBN is like nothing, especially when it's 10 nanometers thick. So, okay. Other questions about How the tech works? Okay, good. So anyway, so let's first just consider what happens if we have a square of graphite. Okay, so the way that we integrate these heterostructures into these circuits, as I mentioned, is we put the heterostructure down first, then we build everything on top. So the waveguide pair, it sits on top of the material, and it's capacitively coupled. Okay, this is also not to scale. This is 10 microns. This is nanometers. So when the terahertz field comes by, it very easily comes down to talk to the sample and to interact with the sample. Okay, so we do the experiment. So we photoexcite this central switch. This is the empty reference arm. This terahertz pulse, when it passes by, it shakes the carriers in our sample, modifies that pulse, and then we can detect these downstream in parallel using these two photoconductor switches. So here's what our data looks like. So you can see the black trace. This is the reference trace. This is what propagated to the right. So this is just a nice, clean, single-cycle terahertz voltage pulse. So this is the amplitude in field, and this is the time. But you can see the pulse that went over the sample is both dramatically reduced in amplitude, and there are additional dynamics that show up. Now, the way we extract the conductivity of the sample is basically the same as you do in far-field time-domain terahertz spectroscopy. So what you do is you Fourier transform these two signals, and we get something that looks like this. Then you take the ratio of these things, multiply by some constants, and out pops both the real and imaginary part of the optical conductivity. Now, what you will notice here...
Sorry, James, please.
What is the distance between the sample and the source in picoseconds? Because I'm thinking if you can have...
Oh, yeah, reflections.
Back
yeah,
and
so
forth reflections.
Yeah, so it's, we engineer it to be on the order of back distance between 20 and 50 picoseconds.
So we don't see it in this picture?
Yeah, oh, no. Yeah, so that circuit, the circuits are many, many millimeters long, which is intentionally to reduce reflections. So yes, all of that is very carefully considered, because yeah, once you get a reflection, you're sort of stuck. That's the end of your bandwidth. So yeah, there is a couple millimeters between the terahertz source and then the sample, then another few millimeters until the detectors to really delay these reflections until as long as possible. Okay, yeah, good technical question. Anyway, so you can clearly see that we do not see a Drude response. This is what I was expecting originally. This is what you would see in a far-field terahertz experiment on a piece of graphite. What we see is a textbook Drude-Lorentz response, where you can see the conductivity really goes to zero at zero frequency. And so what this means is that we clearly have some kind of resonance that we're detecting in our sample. And what's happening is as the terahertz field comes by, the electric field pushes all of the carriers to the edge of the sample, where they pile up. This creates an electric field in the opposite direction, which acts as a restoring force, and this triggers a plasma oscillation. And so this example I just showed, this would be the half wavelength plasmon standing wave. This is the lowest order mode that you can get. And so, what this means, the takeaway message is that these tiny sub-wavelength samples, they naturally act as terahertz self-cavities. And so you're going to get polaritons bouncing off the walls if the sample's small enough in different harmonics. And you can tune the properties of these cavity modes, obviously by changing the material properties. The dielectric environment is also important. The geometric dimensions, of course, if you make the guitar string longer, then the wavelengths get longer. So there's ways that we can tune these cavity modes. Is that a question or an amount of time?
It's a question. So now let me think. The current is along the strip line, right?
No.
You have electric fields that are transverse and currents this way.
No.
Okay.
What we are measuring is, as I showed in my little animation here.
Yeah.
So the terahertz is going along the waveguides into the screen. But the
how is that polarized? Oh, right.
Oh, the field is going, I've drawn the field. So it's going into the screen, but the electric field is shaking left and right on the screen.
But there is also a current that goes with the terahertz that is going into the screen.
No.
9. Okay. No. All right, very good.
Everything we measure is only orthogonal. So it's like the pulse comes in and it sets up plasmons going this way, but then the pulse keeps going by.
James, I also have a question. Shouldn't a plasmon give you a Drude response? Because if you see a Lorentz oscillator displaced at a finite frequency, that indicates to me that it should be some kind of phonon or something.
No, it's definitely a plasmon.
I'm not disagreeing with that, but if I just take an epsilon of 1 minus like omega p squared over omega squared, I'm going to get a Drude Lorentz. I'm going to get a Drude peak. That's not. If I just take my basic solid state textbook, I'm going to get a Drude peak. That comes from the plasma.
This could be, okay, it could be because this is a finite size effect plasmon. That's definitely part of it, because you have to modify the optical constants to realize that you have this extra restoring force. It's not just like an infinitely large solid, it's a subwavelength particle. So I think when you fold that in, everything changes. Yeah, and I'm not the first. I'm not the first to see this kind of thing. Actually, I think June has seen this in nanotubes. You've seen plasmonic responses, and I think you could explain it in the very same way. Anyway,
So-
happy to talk about this later.
So James, the reason why you don't have a current going into the plane is that you don't have a central line. It's just you only have two.
Yeah, exactly.
Because it's a coplanar.
Yeah, or the coplanar would have three, but it's
That's right.
yeah,
It's only
the
two,
parallel,
right?
Yeah, I don't know what.
Yeah, whatever this
I don't
thing
know
is
what
called.
even
But because if you had three, then you would be
Then it
like
would go both
it would be
ways.
like a coax. Okay,
Yes,
got it.
exactly. Yeah.
So just
Yeah.
to finish the last question. So basically that's the bulk response, but you have a finite system. So basically you solve the Maxwell's equation with the bulk susceptibility, right?
Yeah.
Yeah.
Yeah. Exactly. Okay. Anyway, okay, so we'll watch the great movie again. All right, there it goes. There's our standing wave. Okay, so what this means is if you want to study the terahertz dynamics of these tiny van der Waals heterostructures, which we do just because all the quantum phases are there, regardless of cavity physics, this means it's inherently a cavity electrodynamics problem. Doesn't mean it has to be a cavity control problem, but it is a cavity problem because of the finite size effects. Okay, so going back to this result, so what this means, I just took a standard issue flake of graphite, the same kind of flake that the vast majority of van der Waals heterostructures are built on. This flake has a cavity plasmon resonance at 2 MeV, exactly at the energy scale where all of these quantum phases are happening in the materials that are literally sitting 10 nanometers above them.
So I guess you're going to show us this thing should scale like the square root of the density.
Yeah, we'll get there. So okay, you already know where the talk is going, yes. Okay, so going back to that question I raised earlier, how do we put these van der Waals heterostructures in terahertz cavities? The answer is you don't, because they already are literally sitting on top of a pretty good terahertz cavity. So the new question is then, are they coupling? Are these built-in cavity modes in your standard issue backgate, is that coupling to electrodynamics in the 2D material proximatized 10 nanometers above? Okay. So we wanted to look into this. So we're now going to look at a full heterostructure, and this is the simplest possible heterostructure, monolayer graphene, encapsulated in HBN, sitting on top of a graphite gate. One thing I should point out is the plasma frequency of these graphite gates. These are 2D plasmons, so we can tune the frequency with dielectric screening. So basically, the farther we move this away from the sample and the metal waveguides, the higher the plasma frequency gets. So for this device, we've intentionally parked the plasma frequency at fairly high frequencies outside of our experimentally detectable bandwidth. And the reason we did this is we wanted to then see, can we see what the graphene electrodynamics will do without this cavity mode sitting in the middle of our bandwidth. So this is what the measurement we get. So this is with the graphene. Oh, and this is also the backgate, so we can shuffle charges between the two and tune the Fermi level. So this is what we get when the graphene is tuned to charge neutrality. And so this is the rising edge, frequencies on this axis now, conductivities on this axis. So this is the rising edge of the graphite plasmon, which should be peaking somewhere over here.
That's sigma 1.
This is sigma 1. We also have sigma 2, but I'm only showing sigma 1 here. Okay, but now what's interesting is when we gate the Fermi level, increase the carrier density in the graphene, we start to see all of these resonances show up on top of this background. And you'll notice two things. So first, obviously these are going to be graphene plasmonic standing waves. So that's what we're seeing here. And so you see a few things with these resonances. One, as you increase the carrier density going from blue to red, the spectral weight increases, which makes sense, and they are also blue shifting to higher frequency. Okay, so let's analyze this. So in general, it's very well known that in graphene plasmons, the frequency of plasmons should scale as a carrier density to the 1/4 power, which you can just see from this relationship down here. It just has to do with the Dirac dispersion. And so if we had our monolayer graphene in this situation without any cavity coupling physics involved, this is what all of these modes that we see should scale as, n to the 1/4. So now you can see why I'm plotting the data sideways, because now we can compare the frequency versus carrier density, and now the color map here is the conductivity. So you can see that this lowest order resonance that we see, this does scale pretty close to n to the 1/4, as you would expect. But what we find is that when we look at these higher order resonances, the scaling is heavily suppressed from what's expected. So we didn't understand this, and so we worked with Marios from Angel's group, who over the course of a couple of years, really working intimately with us over many, many devices and iterations, he developed this wonderful analytic theory to predict what you should see in an on-chip terahertz experiment. And you can see that his theory agrees pretty well with what we measure in experiment, including the suppressed couplings. But what's nice about the theory is that it's just in Mathematica, so if you want to see what's happening at higher frequencies, you just go to higher frequencies, and you can see what happens when the graphene modes intersect the graphite cavity mode, that they are in fact hybridizing in approaching the ultra-strong coupling regime. And it's this hybridization, one of the consequences of this hybridization up here is the suppression of these other polariton branches in their carrier density scaling. Okay, so we know that the suppression we observe is coming from the fact that the graphene plasmons are coupling strongly to the graphite backgate. Okay, but we wanted to see, could we see this directly within our bandwidth? Yeah.
Is there an easy way to understand why this? Sorry. Is there an easy way to understand why the scaling of the higher modes is different with the density?
Of why it's suppressed? Is there an easy way?
Yeah, why only the lowest one scale with N2?
So I think there's a few reasons. I mean, clearly, this mode down here, okay, look in the simulation because it's easier. This is the black line here is the graphite cavity mode. So you can see this mode down here, there's like no spectral overlap. There's no spectral weight in the cavity mode, so that's why that mode is not really affected. But as soon as you start to have some spectral weight in the cavity mode, that's when you start to see the suppression happening. So if you're, I have 3 minutes left. Okay, I gotta keep going. I'm almost done though. Last device. So we built a second device. So this device, we now intentionally centered this graphite cavity mode right in the middle of our bandwidth. So it would be directly on top of the 3 graphene modes. So that means that the spectrum that we measure, we expect to be inherently more congested, which it is. But if we, so here I'm showing a handful of carrier densities. But if we fit this very, very carefully and transparently, what we find is that we can fit the data well. And if we fit each of these Lorentzians versus the carrier density, we get things like we've seen before. Once again, the lowest order one, n to the 1/4 is fine. And then they become suppressed as you go up. But what's interesting is we can now start examining what's happening when you're crossing the cavity mode frequency. And what we find is that there is, in fact, an avoided crossing that's forming. And from the size of this avoided crossing, we are, just barely into this ultra-strong coupling regime. We've exceeded this 10% threshold. Another interesting feature is that we see a spectral weight transfer. And so here, at the lowest carrier density, this purple Lorentzian here, this is mostly the cavity mode character. And then you can clearly see as we start to gate the carrier density, we are taking spectral weight out of this mode and putting it into the pinkish mode here. And so here's the graph where you can really see these two modes are exchanging their spectral weight. This is what most clearly shows that this is the result of Marios' simulation. So here you can see the avoided crossing forming, which agrees with our data. You can also see the spectral weight going from this mode to this mode, which is consistent with this data that we see here. And so we see these sort of two signatures, this anti-crossing and the spectral weight transfer in this device. Okay, so now the million-dollar question is, what's causing this cavity coupling? So I've said they're all in cavities, and I've showed that at least in the devices we've measured, they're in this ultra-strong coupling regime, your standard issue, device. Now, what we found is that our waveguides actually play a really critical role in determining the coupling strength. They are part of the whole cavity system. And so what happens is if you have a waveguide geometry like this, so this is, in this device, it's 3 microns, this is also 3 microns, and that's 3 microns, maybe there's like a couple microns here and here. What this does is the gold provides, it's a pattern dielectric. It gives you an inhomogeneous screening environment for the plasmons. And long story short, this gives you momentum scattering pathways that turns on coupling between these modes and the two layers of different momenta. And that's how you get this ultra-strong coupling. But if you were to build a device where you make this gap very, very small, this effect completely goes away. And you can really sense the unperturbed cavity electrodynamics, but not cavity-coupled electrodynamics of the sample of interest itself. So this means that moving forward, we now have two avenues for using this technique. So avenue, if we want to study all this, great physics, these quantum phases and these kinds of van der Waals material. So avenue one is this cavity sensing geometry. So if we make this gap small, all this coupling goes away, and then you can just sort of do equilibrium spectroscopy of quantum phases to sort of understand how they work. But if you were to keep doing experiments the way that we're doing, where you have this pattern dielectric environment, you get this ultra-strong coupling regime, you could start doing experiments where you try to manipulate the ground state properties, and look at things like superconductivity, enhance, all these different things. And the way these experiments would work is you would do a DC transport measurement, similar to how Jerome is doing it. But then if you see something different, the way you understand, you could then do on-chip teraspectroscopy to see how the modes are coupling in the background, how energy is flowing, and this could give you a hint if it's cavity physics or something else causing the change. And this is the end. Like I said, we are doing this at millikelvin temperatures. Jerome, we can talk about the details of how to manage heat loads, but we can get signals, and then we can get down to a base temperature of 300 millikelvin. Anyway, here's the summary. I do want to thank these three again, because this was a hero experiment, and these three deserve a ton of credit for seeing this project through. And with that, I'll stop here and thank you for your attention.
So thank you, James. If everybody's okay, we're going to push 5 minutes into the coffee break, so we got 10 minutes discussion. John first.
Yes. I'm going to get my water bottle.
Yeah, thanks.
I'm listening.
So is it crazy to ask about whether you can either measure basically 0-point fluctuations in the Austin switch geometry, or if alternatively you pump the material and look at basically photon emission down your waveguide?
So 0-point fluctuations would be hard because you kind of need, with these ultra-fast measurements, you need a clock, like a start and a stop, is the stroboscopic measurement. So I think I can't. Maybe Daniela or somebody has ideas, but I don't have any ideas there. But moving in the direction of single photon detection and generation is something we're thinking about. And so those kinds of measurements, I think this general kind of platform is going to be really good for those types of measurements. And I'm funded to do that now, so I'll let you know how it goes.
Okay. Just a comment. I think if you wanted to measure vacuum fluctuation there, or let's say the base fluctuation, you would need to have your amplifier to be to really have the bandwidth of the laser, so 100 megahertz. And that's very hard to have pico amp with this very high bandwidth, because then you would need to do shot-by-shot spectroscopy.
Yeah, so that's not the direction I'm trying to go in myself, but it sounds really hard.
Maybe, yeah, thanks for the very nice talk. So one is how does the anti-crossing compare with the line width, and what size the line width of the mode?
Okay, good question. So the line width is not great in these measurements. Now, fortunately, thanks to how the pioneers of this field have chosen to define strong coupling versus ultra-strong coupling versus mega-strong coupling, all these things, for ultra-strong coupling, for that definition, the line width doesn't matter, at least according to how it's defined, because as you can see, this is fairly broad. Okay, this is not going to 0, 0's over here somewhere, but the Q factor of a graphite mode is 3 or 4. Now in the graphene, for example, this mode here, it's something more like 7. And what's interesting is if we fit this to just a Drude Lorentz and we can extract a mean free path, the mean free path we get, this would be for the carriers, is 10 microns. The size of the device is 10 microns, which shows that it's ballistic. And that's what's expected for an encapsulated graphene device. So I don't think it has to be limited there, but this is what our data is showing, that the width is consistent with a 10 micron size device. So this may actually be a fundamental limit for this type of design. Does that answer your question somewhat? Okay.
So you showed these nice results with the suppression of the dependence on n. I would imagine you'd see similar suppression in terms of k, the momentum,
Yeah.
and therefore slower group velocity. Do you see the pulses basically going slower through the graph?
The group, we know the velocity. It's heavily suppressed. It's close to the Fermi velocity because it's a very slow plasmon just from the screening environments. That's expected. Now, as a function of k, k is a more challenging. I mean, we are measuring at finite k. Obviously, they're standing waves. And the momentum of the light in our circuit is basically the separation between the waveguides. So that is a tuning parameter we have, but it's like we can go between 1/3 microns to 1/10 microns. It's not like it's
But you measure the group velocity reduction directly.
Yeah, in general, we measure group velocity reduction, and we have that, and that we can see. But in terms of a K, your other question was a momentum dependence. That is not we have to build a new device every time, and because these devices are all 5 to 10 microns, there's only so much we can do. Maybe if we go to a really small gap, we could get, 1 decade of momentum, very, very close to k equals 0, but still finite. But it's a very extremely labor-intensive process to do that, so it's not a realistic thing for us to do.
So, Jim, since you mentioned single photon generation, what would be the source of nonlinearity?
For generation, not sure yet. The detection is easier because you have these like superconducting nanowires that people bias to the edge of critical current. Then you just have a single photon that creates runaway heating, and then you get a resistance spike in the superconductor. That will be a direction.
Have they done this in terahertz frequency?
Not in terahertz. It's been done in the IR.
Yeah. So you want to generate and detect the terahertz?
Yeah, so the generating the terahertz at the single pulse level would just be a classical thing, where we just reduce the power on the terahertz generator, and then you do a statistics counting measurement, and then once in a while you get a single terahertz photon. But actually, we did an estimate because again, I'm funded to do these kinds of things now. And just with our Austin switches, we estimate that we can already generate and detect on the order of 100 terahertz photons, just with our semiconductor switches. So getting 2 orders of magnitude by using these cavity enhancements and superconductors and all these things maybe isn't so crazy. But the generation, I don't know. Maybe you destroy a superconductor and you get, I don't know. But that sounds a little bit harder to get.
Can I? Yeah. I have a question about the perspective, because I'm not sure I understand it correctly. So when you say you want to go with like narrower waveguides,
yeah.
In a sense you would reduce the capacitive coupling to the sample, but that would essentially make the sample invisible.
No.
Do I not understand?
No. So to be clear, we haven't measured this geometry. We can now, it took us a long time to figure out how to build a 50 nanometer gap, which we can now do. We have a device that's actually going to be measured. Maybe it's being measured right now even. We've done a lot of simulations, though, showing that the same simulations that accurately predict, everything that we measure, that show when you reduce that gap to 50 nanometers, it still works.
You still
the
have
field strengths and the couplings, you lose a factor, you gain a factor, but it all kind of balances out, and we actually pick up like a factor of 2 or 3 in signal to noise. Again, according to the finite element simulations. But if you ask me in 3 weeks, I can tell you what our real measurements show on a real device.
I don't know if I missed the part, but could you repeat, if that's the case, what the ingredients were that Marius put in the theoretical model?
Sure. Well, not in its entirety, but what he basically does is okay, this is good. He divides the cross-section of this heterostructure into these different regions. So underneath the waveguide trace is a screened region. This is unscreened, screened, unscreened, unscreened, and then the sample ends here and here. And then it's just literally solving transmission and reflection coefficients. And then he has some clever way of how to couple to the waveguides initially. And then by solving that problem, that's how he can make, all the spectra that agree so well with all of our data.
So it was actually partially answered. I was also curious about Marius's approach. So this is all for solving Maxwell's equation. assuming that it's Drude formula and you have a metal and that's it, right?
There could be some other ingredients in there, but off the top of my head, I don't know. Yeah, Angel will know better.
It's the Drude formula for the metal, which is the gold, and then the standard RPA response for the graphene and the graphite. And then you just have a standard transmission matrix solver of the Maxwell equation.
Thank you. Thank you, Angel. Thank you, Marius, who's listening to us.
Yeah. All right, let's thank the speakers again. And James.